Hello friends, a very happy new year to all of you. Today we shall be discussing the topic of chemical equilibrium. So in the last few classes we have been discussing about the concept of equilibrium, and we said that a system is said to be in equilibrium when it has thermal equilibrium, that is equality of temperatures within the system, so it's at uniform temperature, equality of pressures, that is mechanical equilibrium, and chemical equilibrium, that is equality of chemical potentials. So this is the concept with which we started, and using that we discussed phase equilibrium in the previous classes. So we applied this condition for a non-reacting system where there are multiple constituents that are present in the mixture, and we derived the condition for phase equilibrium, and we looked at and discussed phase equilibrium in the last few classes. So today we will basically be looking at reacting systems, that is systems where the constituents that are present are chemically reacting with each other. So we have all studied in our school chemistry that you take two reactants and they react with each other to form the products. Examples, let us say combustion of methane. So you have methane and you have oxygen. You put them together and give them an adequate amount of energy, activation energy. Let us say you keep it at high enough temperature so that they start reacting. Then the methane and oxygen combine and they form carbon dioxide and water vapor. This is something that we have studied. And we have also understood that there is also possibility of incomplete combustion, and if there is inadequate amount of oxygen available, for example, the oxidation can limit itself to CO and not go to CO2. That's also a thing that we have seen, but we don't know how it actually happens. So to just get a mental picture clear, let's understand that a methane molecule, what does it contain? It has a carbon and 4 hydrogen atoms in it. And an oxygen, what does it have? 2 oxygen atoms present. So if these molecules, for example, come and collide with each other and the collision is energetic enough, then what will happen? First thing that will happen is the bonds will break. Okay. So to expect that in one collision, the oxygen splits into OO and methane splits into CHHH, and then many molecules of oxygen suddenly come and many molecules of CH2O suddenly come, and in one collision they all get rearranged, the atoms get rearranged into COO, that is CO2, and HOO, HHO, that is H2O. This is a too complex a thing to happen in one collision. But very clearly it does not happen that way. So what happens? In one collision, one energetic collision, that collision might be between CH4 molecule and O2 molecule. It might well be CH4 molecule going and colliding against the nitrogen that is present along with the O2 in the air. Or it might be a collision, energetic collision between two CH4 molecules itself. And what happens when there is an energetic collision of that kind? You might have seen this in cricket matches on the field. When there is a mistake that happens, two fielders running towards catching the same ball and collide with each other, they are likely to break something if the collision is energetic enough, right? So basically the bonds can break, but you cannot expect a rearrangement of bonds in just one collision. So what happens is the CH4 might break into CH3 minus and O plus, H plus, right? So it becomes H ion and CH3 ion. Then another collision that might happen, and H ion goes and collides against O2 and becomes a OH ion and a O ion, right? It breaks like that. So now you have a whole pool of H ions, O ions, OH ions that are present there. They go and collide against the other molecules. they break bonds and make bonds and so on. So they get recombined in that fashion. So you have a large number of elemental reactions that typically happen, and eventually all of these radicals that get formed, they are very short-lived and they have to recombine, or they have to break up into something else very quickly. So the reaction happens that way. The only stable molecules are longer lived. Say for example, the reactants, which are CH4O2N2, and the products, which are CO2, H2O, etc. These have a longer life, and so you find that these get converted into those, but there are a lot of things that are happening intermediate, but they are of very short life. That is why it gives you an impression as if the methane and oxygen combine to give CO2 and H2O, whereas actually there is a lot of intermediate things that are happening. This is basically how a chemical reaction happens. Now, if a chemical reaction can proceed in one direction through all of these intermediate steps, it can also proceed in the other direction because of the same steps, right? But then reaction in one direction is favored under certain conditions. Reaction in the other direction is favored under certain other conditions. What do these conditions mean? These conditions would mean the temperature, the pressure, and the concentrations of the reactants that are constituting each of these elemental reactions. So, on the whole, at any given point in time, the reaction might be proceeding in the forward direction at a certain rate, and the reaction might also be proceeding in the backward direction at a certain other rate. Okay? So, if the forward reaction is faster than the backward reaction, then there is a net progress of the reaction from reactant side to the product side. Okay, and as the products get more and more formed, the concentration of the products goes up, so the reverse reaction also goes up in importance. Okay, so then the reverse reaction starts getting faster and faster as you get more and more conversion towards the product side. So as you approach the product side, the reverse reactions become faster, so you would not eventually be able to reach 100% products, but you will need to reach a stage where the forward reactions slow down as you go further because reactants are getting depleted, and the reverse reaction increases because the products are getting formed. So you would meet somewhere on the way where the rate of the forward reaction and the rate of the reverse reaction balance each other, and then if they balance each other, then the rate of conversion from reactants to products equals the rate of conversion from products to reactants. So there is no net reaction that is happening any further. So the composition of the mixture at which this equilibrium comes is called the state of chemical equilibrium. So no reaction really proceeds from 100% reactants to 100% products, but the reactants keep decreasing from 100% towards 0%, and the products start increasing from 0% upwards towards 100%, and somewhere on the way, the conversion of products to reactants, that is the reverse reactions, and the conversion of reactants to products, that is the forward reactions, the rates match, and that is the end of the reaction. After that, the forward reaction and reverse reaction happen simultaneously at the same rates, and therefore there is no further net conversion of reactant to product that happens. Okay. So this is basically what we understand by the concept of chemical equilibrium. Now, what are the conditions under which the chemical equilibrium can happen? Okay, we can use the same concepts that we understood as condition for equilibrium in the previous lectures to demonstrate this. So let us go to the whiteboard and start looking at the condition for chemical equilibrium. Okay, so we'll move to the whiteboard. Chemical equilibrium. Okay, so let us take a simple reaction. Let's say a reactant A and a reactant B combine in a reversible reaction to give a product C plus a product D. Okay, now it may not be that 1 mole of A and 1 mole of B gives 1 mole of C and 1 mole of D. It might be different also. So let us say some nu A moles of A and nu B moles of B combine to give mu C moles of C and mu D moles of D. This is a very general reaction. Let's take a simple example. So CH4 plus O2 gives CO2 plus H2O. If I try to balance this reaction, so there is one C, so there is one O2 that is required for that, and there are 4 O's, so there is 2 O's required for that, so one more O2. So it becomes 2 O2 that is required, and you get 1 CO2 and 2 H2O. Okay, so this is an example reaction. So if this is A, this is B, this is C, and this is D. So A is methane, B is oxygen, C is CO2, and D is H2O. Then mu A is 1, mu B is 2, okay, and mu C is 1, and mu D is 2. Now, actually what happens is that we write these coefficients together on one side so as to get the reaction written in a more generic fashion. So if I take all of them to one side, I'll basically get a reaction like CO2 plus 2H2O minus CH4 minus 2O2 equal to 0 is a form in which you can write the same reaction. So basically these are products and these are reactants. You write them with a negative sign because the reactants are getting consumed and the products are getting formed, and therefore we'll need to write it with that negative sign. Okay. So where were we? Okay. So if we write the coefficients like this, then actually mu A and mu B become negative. So it becomes -1 and -2, whereas the products have a positive value of mu. So this is the way we write, and therefore you then get a symbol which is like summation from I is equal to 1 to n of all the species, mu I into mu I, let us say RPI equal to 0, where RP stands for reactant or product, right? So if it is a reactant, then you have a negative mu, and if it's a product, you have a positive mu. This is the way the reaction is in general represented. Okay. So then what happens is that if this reaction progresses, then for every mu A moles of A consumed, there is mu B moles of B consumed. So there is a unique relationship between them. Similarly, mu C moles of C consumed and mu D moles of D consumed. So suppose there is delta NA moles of A and delta NB moles of B are consumed to form delta NC moles of C and delta ND moles of D. Okay, so then this stoichiometry of the reaction would basically mean that delta NA divided by mu A should be equal to delta NB divided by mu B, should be equal to delta NC divided by mu C is equal to delta ND divided by mu D, because for every mu A moles of A consumed, there is mu B moles of B, mu C moles of C, and mu D moles of D in this reaction. And if mu A and mu B are negative, then delta NA and delta NB are also negative. So this is a positive quantity, this is a positive quantity, this is a positive quantity, this is a positive quantity. This I call it as the reaction progress variable, let us say delta xi. Okay. So then for every delta NA moles of A consumed, delta NB moles of B will be consumed so long as delta NA by nu A is equal to delta NB by nu B, right? You can take an example from here. So if delta NCH4 moles of CH4 are consumed, accordingly there will be 2 delta NCH4 moles of O2 will be consumed. So this is actually delta NO2. Okay, so basically if I divide it by the corresponding stoichiometric coefficients, I'll get this divided by 1 will be equal to this divided by 2, right? So this is basically what I'm saying, and here it's a -1 and here it's a -2, and therefore delta NCH4 is negative divided by -1 will be a positive quantity, delta NO2 is a negative quantity divided by 2 will be the same quantity, and that will form CO2 and H2O will be delta N CO2 will be actually equal to delta NCH4, because for every mole of this there is 1 mole of this, and delta NH2O with a minus sign, of course, right, and delta NH2 will be -2 delta NCH4. Okay, so if I use this, then I should be able to write this expression very clearly. So the reaction progress variable delta xi therefore is equal to delta NCH4 by -1, which is equal to delta NO2 by -2, which is equal to delta NCO2 by +1, which is equal to delta NH2O by +2. That's the expression that you will get here, right? So that is the example that you will get. So this is your reaction progress variable delta xi. Okay. Now in this, very clearly, if delta xi is positive, then the reaction is proceeding in this direction, because then this is negative, this is negative, this is negative, this is negative. If the delta xi becomes so because nu A, nu B are negative and nu C, nu D are positive, by definition the reactant coefficients are negative and product coefficients are positive. So if this delta xi is negative, right, then delta NA becomes positive, delta NB becomes positive, delta NC becomes negative, and delta ND becomes negative, which basically means that the reaction is proceeding in this direction. So this is delta xi greater than 0, and this is delta xi less than 0. Is that right? So the reaction proceeds in the reverse direction when the reaction progress variable is negative, and it is in the positive direction, the left to right from reactant to product, when delta xi is greater than 0. So this is the way in which we write this expression. So then we'll be able to write that in this one, the delta Ni, which is for every species, would actually be equal to nu I delta xi, right? You can write that, because delta Na is equal to nu A delta xi, delta Nb is equal to nu B delta xi, delta Nc is equal to nu C delta xi, and so on. Right? So we started with this very simple example, but we can write this for a very general reaction which is written in this particular form. Okay. So this is your basic expression. Now with this, if I go to the expression for condition for equilibrium, okay. So the condition for equilibrium so at constant pressure and temperature, if I would like to write the condition for equilibrium, then I'll need to write it in terms of G. So I would say dG is the variable, the what do you call the Gibbs function for the reaction. So if there is a reaction happening, there is a certain process happening, then there is a change in G, and this is written in terms of del G by del P into dP, when other things are kept constant, which is T and N are kept constant, plus del G by del T at constant P N into dP and dt, plus del G, this will be summation over all species, summation over I is equal to 1 to N of del G by del Ni into dNi. Okay, and for equilibrium, this should be equal to 0, and for the reaction to actually happen, this should be less than or equal to 0. When it is less than 0, there is a spontaneous reaction happening, there is a spontaneous progress in the process, and equal to 0 is when it goes to 0. So the Gibbs function goes to a minimum at equilibrium. So that is the statement that we have written. So this we also can write in terms of V dt minus S dt plus summation of from I is equal to 1 to n of mu I dni. Okay, so this is something. So this is at T P n J not equal to I. Okay, so that is the basic definition that we write. So this is the expression. So this is dg. Okay, so in this case, if I substitute for dni from this expression for a chemical reaction, the expression for dni is mu I d xi, then we will be able to write this expression as dg is equal to V dP minus S dt plus summation of mu I into d xi. Okay, so basically mu I d xi is dni. So this mu I is corresponding to the species I, and d xi is quantity which is independent of I. So this is from I is equal to 1 to n. Okay, so at constant Tp, dg is equal to summation of mu I into d xi, and this should be less than or equal to 0 for a reaction to progress. Okay, so from this we can actually derive the condition for equilibrium. Condition for equilibrium is dg is equal to 0. That is, the G has already reached a minimum, so it cannot go either direction, because in either direction it has to have an increase in G, and therefore it's in equilibrium, in which case this has to be 0. So summation of mu I, because d xi is arbitrary, summation of mu I is equal to 0 for equilibrium. Okay, so this is a very important condition. So what does this mean? It means that for the reactants, you will have summation over all the reactants of mu r plus summation for all the products of mu p is equal to 0. That is the summation. So this, since these nu r's are negative, they can be taken to the other side. So basically it can be written as summation of minus nu r into mu r. Minus nu r is positive. So summation of minus nu r would be equal to summation of mu p. So summation or negative of summation of mu r will be equal to summation of mu p is the condition for equilibrium. That is, the chemical potential of all the reactants multiplied by the respective stoichiometric coefficient should be equal to the chemical potential of all the products multiplied by the respective stoichiometric coefficients. So if I take the example of this reaction, the CH4 plus 2O2 gives CO2 plus 2H2O. In this one, we'll be able to write this one basically would mean that mu CH4 with a negative sign, because minus nu r will be, okay, minus nu r will be plus 1. Okay, so this is nu r is minus 1, so it will be plus 1, plus 2 mu O2 will be actually equal to mu CO2 plus 2 mu H2O. Okay, so this is the condition for equilibrium. So the reaction will come to equilibrium when this becomes equal to this. So these will change when the pressure and temperature are kept constant. These will change when CH4 concentration and O2 concentration change, right? So as CH4 concentration and O2 concentration decrease, the chemical potential on this side will go on decreasing, and as CO2 and H2O increase, the chemical potential on this side will go on increasing, eventually until such time that they become equal to each other. So if we try to write or draw it pictorially, then what will happen? Let's say we have the reaction progress variable xi in this axis. Okay, so the reaction rate of reactant species will go on decreasing as we go. So if I write summation of mu I, okay, for the reactants it will be maximum when it's pure reactants, and for the products it will be 0. So it will start decreasing like that and go on. So this is for the reactants. And for the products, it will start with very small value and go on increasing and go like that. So there will be a certain value of xi, or the reaction progress variable, at which this is for products. Okay, so this is the mu I for products, and this is the mu I for reactants. So at some point they both will be equal, and that is the position of the equilibrium condition. So this is the equilibrium condition. So when the xi goes on increasing from let's say 0, where the reactants it's completely reactants, it goes on increasing and reaches this value. So until this value, the reactant production rate, the reactants chemical potential was higher, and as you go this side, the product chemical potential is higher. Okay, so the difference between these two is your expression for summation of mu I that you actually talked about, right? So if I call this as a variable, let us say A, the normal A we have used for Helmholtz function. So we'll call this cursive A. So let's call this as A. So A is basically the summation of mu I, which is mu I of products minus mu I of reactants. The mu is negative for reactants. Then we actually get the A will be this, and here. So what happens? Here the products is higher, the reactants is lower, so A is greater than 0, and oh sorry, I had to actually write it as a minus A in that step. So sorry, the definition is so this I write it as minus A. So A is actually defined as negative of this, which is basically reactant minus product. So this is minus A. So then the inequality will just be reversed here. So this is A less than 0 and this is A greater than 0, and this is the point when A is equal to 0. The A equal to 0 is the equilibrium condition. Okay, and A is greater than 0 because your expression of mu I dg is equal to summation of mu I d psi. So this is minus A d psi, right? So this actually you write it as V dP minus S dt minus A d psi. Okay, this is the expression that you write. So this is basically the dg is equal to minus A d psi, which is less than or equal to 0. So for the reaction, dg is equal to minus A d xi, okay, which should be less than or equal to 0. Now equal to 0 for equilibrium and less than 0 for the spontaneous progress of the reactions. So if d xi has to be positive, then A has to be positive. Okay, so when A is positive, that is here, then the reaction progresses in the forward direction. And when A becomes negative, because the spontaneity condition requires the product to be negative, d xi has to be negative, because minus A d xi. So this basically would become A d xi is greater than or equal to 0 is the spontaneity condition. Spontaneous reaction. Okay, so if A is positive, then d xi also has to be positive for the reaction to actually for a feasible process. If A is positive, then d xi has to be positive, and if A is negative, d xi has to be negative. Which basically means when A is positive, the reaction happens in the forward direction, and when A is negative, the reaction happens in the reverse direction. And finally, they reach a state which is equilibrium state, and at this state A is 0, and therefore the reaction neither goes forward nor goes backward, and it stays here. Right? So this is the condition for chemical equilibrium. So we can actually see from this expression that this is del G by del P, this is del G by del T, and therefore this has to be del G by del xi with a negative sign, right? So you can say that A is nothing but minus del G by del xi at constant Tp. Okay, so this is your expression for our definition for A. Okay, so this minus del G by del xi at constant T and P, this is your expression for A. Okay, so if I take this definition, dG is equal to V dP minus S dt minus A d xi, we'll be able to derive from the other property relationships. So I write dG is equal to V dP minus S dt minus A d xi. Then we should be able to, from the definition of dG, this is G is H minus Ts, so we can write dH minus T ds minus S dt is equal to V dP minus S dt minus A d xi. Okay, so the S dt cancels on these two sides, and the TdS can be brought this side. So dH becomes equal to TdS plus V dP minus A d xi. Okay, so in the same way you can define du. So you can write dH as du plus P dV plus V dP. So the V dP would get cancelled, so it will actually become TdS minus P dV minus A d xi. And similarly dA, this is to note the difference between the two A's in writing. Okay, this is the Helmholtz function. Okay, so this is U minus Ts, so du minus TdS minus S dt. So if the TdS would get cancelled, the S dt would come here. So minus S dt minus P dV minus A d xi. So from all this, you'll be able to write that A is equal to minus del G by del xi at constant Tp, which is equal to minus del H by del xi at constant Sp, which is equal to minus del U by del xi at constant SV, which is equal to minus del A by del xi at constant S comma at constant S at constant T comma V, sorry. Okay, so that is your expression that you get. So this is very similar to your chemical potential. This we can call it as the potential for the reaction. So when this potential is positive, then the reaction happens from the reactant side to the product side, and the potential is negative, it actually happens from the product side to the reactant side, and the potential is zero, then it is not happening at all. So this is a definition that you get very similar to the chemical potential definition. So when the chemical, we said that mass transfer happens when the chemical potential is higher, so from the higher side to the lower side. Now in the same way here, the chemical reaction happens from the side where the reaction potential is higher to the reaction potential lower. So the A d xi is in some sense the generalized force, generalized coordinate relationship for a chemical reaction to happen, right? So that's the way it is. Minus A d xi. Minus A is the generalized force and d xi is the kind of reaction progress variable. So A d xi is the progress of the reaction. So the change in mu is that. So when A becomes equal to 0, then there is chemical equilibrium. Right? So this is the concept of chemical equilibrium, and we can use this concept to define reaction equilibrium conditions. Okay, so we'll pause at this point and continue in another lecture where I will define equilibrium constant and also tell you methods of evaluating equilibrium constants, how it varies with temperature and pressure and so on, and what are the implications of the definition that we do. All of that about equilibrium constant and equilibrium compositions we will do in a separate lecture. In this lecture, we will stop with the concept of chemical equilibrium and how the reaction progress variable goes in one direction or the other depending on the potential variable A, which is defined in terms of the four energy terms, the Gibbs function, Helmholtz function, internal energy and enthalpy. Okay, so this is where we will stop with the conceptual understanding of chemical reaction equilibrium. Stop here.